Hello everyone, this is chapter 7.2, verifying trigonometric identities. And here we'll basically be given an identity, some expression equals some other trigonometric expression, and we'll be using trigonometric identities to prove these identities. So these identities are going to be a little more complicated than the fundamental ones we've seen so far, but we'll use the fundamental ones to show that these are indeed true. Now, before we begin, I just want to keep two things in mind. The first thing is that identities are true for all values of a given variable. So for instance, if you have this, this equation here, this isn't actually an identity, it's an equation, but it's not an identity. And the big difference, of course, is this is not true for all values of theta, it is only true for some values of theta. For instance, when theta is pi over 6, or even 5 pi over 6, this holds. But if theta is anything else, well, some other things work, but if it's, let's say, 0 or pi over 2, this is not true. Whereas a Pythagorean identity, for instance, is true for all values of theta, no matter which value you pick. So that's really the difference between an identity and, a conditional equation like the one I just showed you. All right, now the second point here is more of like some advice. And basically it's the procedure we'll be using to verify identities. And here I say, to verify an identity, show that each side simplifies to the same expression. That doesn't always mean you'll have to simplify both sides. Usually we'll start with the more complicated side, simplify that as much as we can and show that it'll be equal to this. But if we arrive at kind of a dead end, then we have no choice but to work with both. But for this example here, we'll actually see that only one side works. Well, only one side suffices, really, is what I meant to say. Now, I'm going to do this two different ways. The first way I'm going to show you is by using the identity secant squared minus 1 is equal to tangent squared. Now, that identity actually is from this identity. So remember that when you have a Pythagorean identity, you can manipulate it. And one way I showed you to manipulate it, for instance, to get secant involved, is to divide by whatever you need to get secant involved. So since 1 over cosine is secant, if you divide everything by cosine squared, kind of like I showed in previous videos, we'll get tangent squared plus 1 is equal to secant squared. And if you subtract 1, then you'll get tangent squared is equal to secant squared minus 1, like that. So in fact, we can replace the numerator with tangent squared using this identity, which is a modification of one of the Pythagorean identities. So let me erase this, and let's actually work with this equation using that. So the numerator is replaced with tangent squared, and we're dividing it by secant squared. There's a whole lot of ways you can play this. What I'm going to do is this. I'm going to say that tangent is sine over cosine. Okay, that's the numerator. The denominator is 1 over cosine, so it's 1 over cosine squared. Perfect. Let me erase this. It's getting kind of in the way. And now, of course, what I'm going to do now, it becomes fairly obvious from here. Just multiply the top by the reciprocal of the bottom. Or I guess you can multiply top and bottom by cosine squared, same idea. And we end up getting cancellation, and we get the actual left-hand side, which is what we wanted, so I'll check mark this. So the funny thing about these types of problems is there's no specific answer. The work is kind of our answer. Because it's asking us to verify this identity, meaning we're asked to show that this simplifies to that, or that they each simplify to the same thing, the same expression. So it's kind of weird because they're already telling us this is true, we just have to show it. So verifying is showing. Now again, I wanted to show you another way because in my eyes I see something a little simpler. Here's what I see. So I'm going to write or. I'm going to split this fraction up as secant squared over secant squared minus 1 over secant squared. So again, I'm working with the left-hand side to get the right-hand side. Now notice, secant squared over secant squared is 1. And since the reciprocal of secant squared is cosine squared, this becomes this. And notice this is just a modification of sine squared plus cosine squared equals 1. We saw this actually in 7.1. This is just sine squared, and will allow you to verify that on your own. That this is just a modification of the normal Pythagorean identity that we're used to. And there we go. So I've shown two ways of verifying this. There are probably more, but these I think are the more elementary ways of doing it, kind of the more obvious ways of doing it. So we're going to see more examples, but 7.2 really is just this, the idea of verifying an identity. We'll see some pretty complicated ones, so I want to do a few more examples, so let's take a look at those right now. All right, so for this example, I'm asking us to verify these two identities. They're kind of complicated. So there's a few ways I can actually see to do this one, but the more, I guess, straightforward approach is to just combine the most complicated side, in this case the left-hand side, into one fraction and see what happens. And we kind of saw, I mentioned in the last video for 7.1, when you add fractions you can do this crisscross pattern. So I'm going to show that here. So multiply this to this, I'm going to get 1 plus sine of theta times itself, so that's squared, plus this times this is going to be cosine squared, all over the denominators multiplied. So multiplying opposite denominators to opposite numerators, and then multiplying the denominators to each other for the common denominator. So this is let me just write left-hand side here. And I want to show that this simplifies to the right-hand side. We're almost there, actually. Notice 1 plus sine of theta all squared is a binomial squared. So we know how to do that, hopefully, if we remember that from Algebra 1. That's the first one squared plus 2 times their product plus the second one squared. So what we get is 1 plus 2 sine of theta plus sine squared plus cosine squared, because of this cosine squared. Perfect. And now what? Now I think we're almost there, because what we can tell, hopefully with the last two terms on top, this is just 1. So what we end up getting is those 1's actually combine on top. So this is actually 2 plus 2 sine of theta all over cosine of theta times 1 plus sine of theta. Perfect. And now, of course, if you pull 2 from the top, let me just show that here by erasing. I hate doing that normally, but in a video setting it's okay because you can always rewind, of course. And great, now we notice the 1 plus sines cancel out. We get 2 over cosine. 1 over cosine is secant, so we could bring the cosine up as secant. So we get 2 secant of theta, and that verifies the identity. And there again, I mentioned there are a few ways of doing this. If you want to try to do it a different way, they're just to show you. If you split this up, you get 1 over cosine plus sine over cosine. So that's secant plus tangent. Notice these are reciprocals, so you can write this as 1 over this. And from there, you probably have to combine them. But still, it's not a bad idea to try to get used to doing different approaches so you can get used to, well, the dynamic of verifying identities. Because it's not always the case that one method will always work, but generally what you end up doing is, again, just picking the most complicated side, simplifying it, and you'll get outright the other side. All right, so now moving on to this one. What sticks out to me most is this pi over 2 minus t. So far, everything we've seen have had the same arguments. Remember, argument just means the thing inside of the trig function. But in this case, these are t, but this is pi over 2 minus t. It's different. But where have we seen pi over 2 minus t appear in identities? We have seen the cofunction identities. So a trig function of pi over 2 minus t is the same as the cofunction of this trig function of just t. In other words, cosecant of pi over 2 minus t is just what of t? The cofunction of cosecant, which undoes the co, and you'll just get secant. Good. So really, this is sine of t times secant of t. But what do we know about secant of t? Secant of t is 1 over cosine, and we get sine over cosine h of t. And what do we know about sine of t over cosine of t? By quotient identity, it is tangent of t. And that verifies that identity kind of quickly, but at least I gave you an example there of a cofunction identity, which we hadn't really seen used at all in this section. And I know it's kind of short, but I'm really going to stop here because any other example I can kind of come up with are basically less challenging versions of what I've shown so far. And I think this will be enough for you to explore homework problems in 7.2. And I'll see you in the next video for 7.3. With that being said, Thanks for watching. See you then.